We've come to Gauss's law. Having learned to compute the electric flux, we'll state Gauss's law in words in the following way. The net electric flux, phi sub E, through a closed surface S is equal to the net enclosed charge, Q ENC for enclosed, divided by the permittivity of free space. We call this epsilon naught or epsilon sub zero. It is equivalent to 1 over 4 pi k, where k is the Coulomb constant that we've been using. Some of my previous students prefer to call Gauss's law net flux and chill. You are in chapter 22 of Young and Friedman. As a formula, we can state Gauss's law in the following way. The net electric flux through a surface is equal to enclosed charge divided by epsilon naught. Often we will refer to the left-hand side of Gauss's law here. That's the computation of the flux. We will work this separately from the right-hand side, where we may have some calculations to do to determine how much charge is inside of the surface. Eventually we'll take the left-hand side, set it equal to the right-hand side, and solve for our unknown electric field. Again, when calculating flux, your dA vector must point outward from the enclosed volume V. Right? We just have a arbitrary blob surface S, which encloses some volume here. That dA vector must be perpendicular to the plane that is tangent to the surface at a given point, P. This Gaussian surface we'll refer to is an imaginary closed surface used for calculating electric fields on that surface. And we'll see that Gauss's law is only useful when there is a high level of symmetry in your problem. So the left-hand side of Gauss's law proceeds with a calculation of electric flux, say surface integral of E dot dA over the surface S. So you've seen this in the previous electric flux topic, EdA cosine theta. Theta may vary. In general, it will be different across your surface. When you see this circle on the integral symbol, now we're referring to a closed two-dimensional surface integral, whereas in the definition of flux video, we did not demand that the surface be closed. Closed two-dimensional surfaces enclose a three-dimensional volume. Your right-hand side of Gauss's law, Q enclosed over epsilon naught, may be just a simple sum of discrete point charges, or you may need to integrate over some continuous charge distribution. And you'll work examples of this in class. Gauss's law in practice we're going to use it to find the electric field created by symmetric charge distributions What do we mean by that? Easy shapes. Maybe just a point charge having 0 dimensions. We'll find that we attack those problems the same way that we do with any sphere in 3 dimensions. There will be linear or one-dimensional charge distributions And you'll see that we attack those in the same way as three-dimensional cylinders. The final symmetry that we can use Gauss's law for is a flat plane, or a flat plane being two-dimensional, or a slab being three-dimensional. To find the electric field at some point P, follow these steps. First, identify the symmetry. If it doesn't fall under one of these three categories, you cannot use Gauss's law to solve for that electric field. Step 2 will be to choose a Gaussian surface. We'll call it S, such that point P, where we want to know the field, resides on that surface. We'll demand that the surface S encloses at least a portion of the charge distribution if you're talking about an infinite object, or all of the charge if we're dealing with a finite object. Our surface must also cause this dot product, E dot dA, on the surface S must be easy to calculate, meaning the angle between E and dA theta should be constant. It's not changing as you're going across the surface. And it's usually 0 degrees, 90 degrees, or 180 degrees. That makes this dot product easy. In those three cases, E dot dA will either be plus EdA. When you bring in the cosine of 0, that's a plus 1. 0 when you bring in the cosine of 90, or negative EdA. The cosine of 180 brings the minus sign. Finally, to find the electric field, the last step will be apply Gauss's law. In other words, we just write down that the left-hand side equals the right-hand side. And solve for the magnitude of the E field. Let me show you a quick example. We start with a problem where the answer is already known to us. Simplest case you can do is a point charge. We already know its electric field. We want to make sure we're using Gauss's law properly. X, Y, Z axes this way. We'll place a positive point charge here. Just call it plus Q. What we want is to choose a surface S such that E dot dA is constant and uniform, and that dot product should be easy. Well, what does the E field from a point charge look like? It points away from a positive charge radially. A reasonable choice would be, let's surround the point charge with a sphere. What is the dA vector on that sphere, on the surface S that we've chosen? Surface dA perpendicular to that surface points radially outward. It's the nice feature of the spherical surface. E dot dA is going to be easy because regardless of what dA we select, the E field pointing away from that positive point charge will always be parallel to the dA vector. So here Gauss's law, left-hand side is electric flux, right-hand side is Q enclosed over epsilon naught. Our left-hand side is straightforward. On the surface S, we must integrate E dot dA. What's our angle between every E and dA that you can pick on that surface? It's 0 degrees. So we have integral over S, E dA cos 0, which is 1. Because E is parallel to dA everywhere on S. It's important that you justify each simplifying step of Gauss's law to earn full credit. Here, the next simplifying step to take is the following. On the surface S, of course, the electric field vector is changing its direction everywhere, but its magnitude is uniform on S. Because E magnitude is uniform on S. And be careful to understand we're not saying that E vector is uniform. It's changing its direction everywhere on the surface, but its magnitude is uniform. Therefore, we can take it outside of the surface integral. It does not depend on location across the surface. Well, the next step then is to say, what is the sum, the integral sum of all of these little bits of area dA all over that surface? There's an infinite number of them, and I'll sit here and wait for you to count them. And then you can say, wait a minute, the surface area of a sphere is 4 pi r squared. All of those bits of area have to add up to the total surface area of a sphere. Now you can go, if you're feeling particularly mathy, you can express the dA in spherical coordinates, r squared cos theta d phi d theta, where theta is your angle down from the z-axis, and phi is your angle swinging around the z-axis. You could compute the 4 pi r squared that way. The surface area of a sphere is gotten by integrating over this dA. But we do not require multivariable calculus for this course. So you can just skip to say that the total surface area is 4 pi r squared for a sphere. The right-hand side, this is the shortest that it will ever be. In this problem, the only contained charge in your sphere is the plus q point charge. Now we set left-hand side equal right-hand side. On the left we have e 4 pi r squared. On the right we have plus q on epsilon naught. We solve for the magnitude of e. Q over 4 pi epsilon naught r squared. And because epsilon naught is 1 over 4 pi k, 1 over 4 pi epsilon naught is k. What we see is the electric field magnitude for a point charge, kq over r squared, that we know and love. E is a vector, so you should think about its direction. Here, the given charge was positive, so it will simply point radially outward.